advancing the final frontier, pioneering interstellar travel to explore distant galaxies. In the ever-expanding realm of human exploration, the desire to travel through space at astonishing speeds and reach far-flung galaxies has captivated the minds of scientists, engineers, and dreamers alike. While the vast distances between celestial bodies pose significant challenges, recent advancements in theoretical physics and propulsion technology have sparked renewed hope for achieving interstellar travel. This article delves into the possibilities, challenges, and potential methods for realizing humanity's ultimate ambition, to venture beyond our solar system and journey to other galaxies. The limitations of conventional travel. Traditional space travel, even at the speed of light, would take centuries to traverse the immense distances between galaxies. Our current fastest spacecraft would require tens of thousands of years to reach the nearest neighboring galaxy, Andromeda. To overcome this seemingly insurmountable obstacle, innovative solutions are required. Warp drives and Alcubierre theory. One promising avenue for interstellar travel involves the theoretical concept of a warp drive. Inspired by physicist Miguel Alcubierre's groundbreaking work, the Alcubierre drive proposes bending space-time around a spacecraft, creating a warp bubble that moves the vessel within it. By compressing space in front of the ship and expanding it behind, the ship could effectively ride a wave of manipulated space-time. While the concept is exciting, the challenges of creating and harnessing the required exotic matter to achieve this manipulation remain formidable. Ion propulsion and beyond. In the realm of existing technology, ion propulsion stands as one of the more feasible options. Ion engines utilize electric fields to accelerate ions, providing gradual but continuous thrust. This method has been employed in various space missions, such as NASA's Dawn spacecraft. While not capable of achieving relativistic speeds, ion propulsion could potentially be used in combination with other technologies to reach nearby star systems within a human lifetime. Breakthroughs in propulsion. Recent breakthroughs in propulsion have sparked intrigue and optimism. Concepts like nuclear, thermal propulsion and fusion drives hold the potential to drastically reduce travel times. Nuclear, thermal propulsion involves using nuclear reactors to heat propellant and expel it at high velocities, while fusion drives would tap into the energy generated by nuclear fusion reactions. However, both approaches are still in their infancy and present numerous engineering and safety challenges. Interstellar arcs and generational ships. Given the limitations of our current technology, another approach to interstellar travel is the concept of generational ships or interstellar arcs. These enormous vessels would house multiple generations of travelers who would live, work, and reproduce during the journey. While this idea addresses the time issue, it introduces complex social, psychological, and ethical considerations related to long duration space habitation. The role of quantum mechanics. Quantum mechanics, a field known for its counterintuitive properties, might hold the key to faster than light travel. The phenomenon of quantum entanglement, where particles instantaneously affect each other regardless of distance, has led to the exploration of quantum teleportation. Although teleporting physical matter remains speculative, the potential for transmitting information using quantum entanglement could revolutionize communication between distant spacecraft. The road ahead. Interstellar travel, once confined to the realm of science fiction, is gradually inching toward the domain of scientific reality. While we have yet to unlock the secrets of manipulating space-time or harnessing exotic matter, the convergence of theoretical breakthroughs and technological innovations offers a glimmer of hope. Humanity's thirst for exploration and discovery has driven us to conquer seemingly insurmountable challenges throughout history, and the quest to traverse the vast cosmic expanse to other galaxies is undoubtedly the next frontier waiting to be conquered. As we stand on the precipice of a new era of space exploration, one thing is clear: the journey to the stars will demand unparalleled collaboration, ingenuity, and determination. While we may not yet have all the answers, our unwavering commitment to pushing the boundaries of what is possible guarantees that the story of humanity's interstellar odyssey will be one for the ages. Remember, the stars may be distant, but they have never been closer to our reach. So we will go more in detail. The astronomical distances. Space, as we know it, is vast beyond comprehension. The distances between celestial bodies are Measured in astronomical units, O, the average distance between the Earth and the Sun. For reference, Earth is about 1 astronomical unit away from the Sun, which is roughly 93 million miles. The nearest star system, Alpha Centauri, is approximately 4.37 light-years away, equivalent to nearly 25 trillion miles. And even our closest neighboring galaxy, Andromeda, is a staggering 2.537 million light-years away. Speed of light limitation. Conventional space travel, even at the speed of light, which is roughly 186,282 miles per second or about 670 million miles per hour, is far too slow to traverse the distances between galaxies in any reasonable time frame. As an example, let's consider our journey to Andromeda. If we were to travel at the speed of light, it would take over 2.5 million years to reach our destination. This limitation stems from Einstein's theory of relativity, which states that as an object's velocity approaches the speed of light, its mass increases exponentially, making it increasingly difficult to accelerate further. Energy requirements. To achieve speeds near the speed of light, an immense amount of energy would be needed. Conventional rocket propulsion systems, like those we use today, are simply not capable of reaching such velocities. The amount of fuel required would be astronomical, making the spacecraft itself prohibitively large and heavy. Additionally, the energy needed to accelerate and decelerate such massive objects to relativistic speeds is currently beyond our technological capabilities. Time dilation. As we approach the speed of light, another phenomenon known as time dilation comes into play. According to Einstein's theory of relativity, time slows down for objects traveling at high speeds relative to stationary observers. This means that even though travelers might experience a relatively short passage of time on their journey, more time would pass on Earth. This effect becomes more pronounced as speeds approach the speed of light. While time dilation has been experimentally verified with subatomic particles, applying it to human space travel introduces complex challenges related to biology, psychology, and communication. Microscopic space debris. Space is not an empty void, it's filled with tiny particles and debris that could pose a significant threat to spacecraft moving at high velocities. Even a small particle colliding with a spacecraft at near light speeds could cause catastrophic damage. Shielding against such debris would be a formidable engineering challenge, further complicating the design and safety of interstellar vessels. Cosmic radiation. As we venture out of the protective magnetic field of our solar system, interstellar travelers would be exposed to higher levels of cosmic radiation. Prolonged exposure to this radiation could have harmful effects on human health, including an increased risk of cancer and damage to vital biological systems. Developing effective shielding against cosmic radiation remains a critical concern for long-duration space travel. In summary, the limitations of conventional space travel are rooted in the vastness of interstellar distances, the insurmountable energy requirements to achieve relativistic speeds, the effects of time dilation, the challenges posed by microscopic debris, and the risks associated with cosmic radiation. These challenges have compelled scientists and engineers to explore novel concepts and theories, such as warp drives, ion propulsion, and generational ships, in order to overcome these limitations and pave the way for humanity's eventual journey to other galaxies. Now we will go to warp drives and Alcubierre theory. Let's delve deeper into the concept of warp drives and the Alcubierre theory, exploring how they could potentially revolutionize space travel and their implications for exploring distant galaxies. Warp drives and Alcubierre theory. The idea of a warp drive, as popularized by physicist Miguel Alcubierre, involves bending space-time around a spacecraft to create a warp bubble. This bubble would move the spacecraft within it, effectively allowing the vessel to travel faster than the speed of light without violating the laws of physics. The concept is reminiscent of science fiction, but Alcubierre's theory was based on the principles of general relativity and the curvature of space-time. How it works. The Alcubierre drive proposes that space-time in front of the spacecraft is contracted, while space-time behind it is expanded. This contraction and expansion create a wave that carries the spacecraft within the warp bubble. Because the spacecraft itself isn't moving at relativistic speeds, it avoids the energy limitations associated with directly achieving those speeds. Implications for space travel. The Alcubierre theory offers tantalizing possibilities for interstellar travel by circumventing the limitations imposed by the speed of light. If a warp drive could be engineered and harnessed, it would revolutionize space exploration in the following ways. 1. Traveling faster than light. By creating a localized warp bubble, a spacecraft could potentially traverse vast distances in space. Time at speeds greater than the speed of light, drastically reducing travel times. 2. Avoiding time dilation. Since the spacecraft itself isn't moving at relativistic speeds within the warp bubble, the effects of time dilation might be minimized or even eliminated. This would address the challenge of time passing differently for travelers and those on Earth. 3. Reduced energy requirements. The energy requirements for achieving the warp bubbles expansion and contraction are theoretically feasible compared to the infinite energy needed to reach the speed of light conventionally. 4. Exploring distant galaxies. With a functional warp drive, the vast distances between galaxies could become traversable within a human lifetime. This would open up the possibility of exploring and studying other star systems and galaxies in detail. Challenges and limitations. However, the Alcubierre theory also presents significant challenges and uncertainties. 1. Exotic matter. The creation and manipulation of the required exotic matter with negative energy density, which has repulsive gravitational effects, remain theoretical and have never been observed in practice. 2. Stability and control. Maintaining the stability and control of a warp bubble would be complex, as well as preventing it from collapsing catastrophically. Theoretical calculations have raised concerns about potential high-energy interactions at the bubble's boundaries. 3. Potential paradoxes. The creation of a warp bubble could lead to causal paradoxes, such as time loops or the possibility of traveling back in time. Resolving these paradoxes is a fundamental challenge. 4. Ethical and safety concerns. Just as with any groundbreaking technology, there would be ethical considerations and potential risks associated with testing and deploying a warp drive. The future of warp drives. While the Alcubierre drive concept ignites imaginations, it's important to note that its realization is currently far from certain. Progress in understanding exotic matter, developing the necessary engineering solutions, and addressing the theoretical challenges is still needed. Some physicists are exploring alternative approaches to achieve similar effects, such as the warp bubble concept put forth by physicist Harold White, which aims to minimize the energy requirements. In the quest to master spacetime manipulation, it's clear that the journey toward a functional warp drive will require a convergence of cutting-edge physics research, innovative engineering solutions, and a deepening understanding of the fundamental nature of the universe. While we may not yet be at the stage where warp drives are a reality, the pursuit of such transformative technology underscores humanity's unquenchable curiosity and determination to explore the cosmos. Let's dive deeper into ion propulsion and its potential impact on faster space travel, including its relevance for intergalactic journeys. Ion propulsion. Ion propulsion is a type of spacecraft propulsion that uses the principle of accelerating ions, charged particles, to generate thrust. Unlike traditional chemical rockets that expel hot gases for propulsion, ion engines use electric fields to accelerate ions to high velocities, resulting in a gradual but continuous thrust. This technology was initially developed in the 1960s and has gained renewed interest for its potential applications in deep space missions. How ion propulsion works. 1. Ionization. A gas, often xenon, is introduced into the ion engine's chamber. Electrons are stripped from the gas atoms, creating a cloud of ions and electrons. 2. Acceleration. The ions are then accelerated by an electric field. This electric field gives the ions significant kinetic energy, propelling them out of the engine at high speeds. 3. Exhaust. As ions are expelled from the engine at high velocities, they create thrust in the opposite direction, in accordance with Newton's third law of motion. Advantages of ion propulsion. 1. High-efficiency ion engines can achieve much higher exhaust velocities compared to traditional chemical rockets. This results in greater fuel efficiency and a higher specific impulse, a measure of propulsion efficiency. 2. Constant thrust. Ion engines provide a constant low-level thrust over extended periods. While The thrust is modest, this continuous acceleration can build up significant velocity over time. 3. Fuel conservation. The efficiency of ion propulsion means that less propellant is needed to achieve the same change in velocity compared to chemical rockets. Impact on space travel. While ion propulsion has been used in various space missions, including NASA's Dawn spacecraft and the ESA's Bepicolombo mission to Mercury, its impact on intergalactic travel is significant. 1. Accelerating over time. Ion engines, while not capable of achieving relativistic speeds, could be used to gradually accelerate spacecraft over extended periods. This gradual acceleration would allow a spacecraft to reach higher velocities, making it feasible to reach nearby star systems within a human lifetime. 2. Fuel efficiency for long journeys. Intergalactic journeys require immense distances to be covered. Ion propulsion's fuel efficiency would be crucial for these extended missions, as it reduces the need to carry vast amounts of fuel. 3. Minimizing fuel mass. Carrying large amounts of fuel is impractical due to the energy requirements for acceleration. Ion engines, by conserving fuel mass, would enable spacecraft to carry more scientific instruments and equipment for exploration. 4. Combining with other technologies. Ion propulsion could potentially be combined with other propulsion technologies, like nuclear thermal or fusion propulsion, to achieve higher speeds. This combination could significantly shorten travel times to distant galaxies. Challenges and considerations. Ion propulsion is not without its challenges. The relatively low thrust produced by ion engines limits their use for missions requiring rapid changes in velocity, such as launches from planetary surfaces. Additionally, the power requirements for ion engines necessitate efficient power generation systems for deep space missions. Conclusion. Ion propulsion offers a promising avenue for making intergalactic travel more feasible. While not capable of achieving relativistic speeds on their own, ion engines can play a crucial role in gradually accelerating spacecraft over extended journeys. Combining ion propulsion with other propulsion technologies and innovative approaches could hold the key to significantly reducing travel times to other galaxies, making the dream of exploring the cosmos a step closer to reality. Let's delve into the fascinating realm of breakthroughs in propulsion and the potential impact on space travel, especially for intergalactic journeys. Breakthroughs in propulsion. Recent advancements in propulsion technology have the potential to revolutionize the way we travel through space. These breakthroughs seek to overcome the limitations of conventional rocket engines and propel spacecraft at higher speeds, thereby reducing travel times and enabling us to explore distant galaxies more effectively. Nuclear thermal propulsion. Nuclear thermal propulsion is a concept that harnesses the energy from nuclear reactions to heat a propellant, typically hydrogen, to high temperatures. This superheated propellant is then expelled at high velocities to generate thrust. Compared to chemical propulsion, nuclear thermal propulsion offers significantly higher exhaust velocities and thus better fuel efficiency. Implications for space travel. 1. Faster acceleration. Nuclear thermal propulsion can provide greater thrust and thus accelerate spacecraft at higher rates. This enables quicker exits from planetary gravity wells and accelerations toward desired destinations. 2. Reduced travel times. With higher exhaust velocities, nuclear thermal propulsion could dramatically reduce the time needed to reach distant galaxies. For example, a spacecraft equipped with nuclear thermal engines could reach nearby star systems in a fraction of the time it would take using conventional chemical propulsion. Fusion propulsion. Fusion propulsion involves generating energy by fusing atomic nuclei together, which is the same process that powers the sun. If harnessed effectively, fusion propulsion could provide a virtually limitless and highly efficient source of energy for space travel. Implications for space travel. 1. Unprecedented energy. Fusion releases energy far greater than conventional chemical reactions. This energy could be used to heat propellant, generating tremendous thrust and enabling much higher speeds. 2. Shorter travel times. Fusion propulsion could potentially enable travel at a significant fraction of the speed of light. This would drastically reduce travel times to distant galaxies, making intergalactic exploration more practical. Examples in action. 1. Project Daedalus. In the 1970s, the British Interplanetary Society conceptualized Project Daedalus, a fusion-powered interstellar spacecraft. While never built, this ambitious design laid the foundation for future fusion propulsion concepts. 2. Project Breakthrough Starshot. This project aims to send a fleet of small, lightweight spacecraft to the Alpha Centauri star system using a laser-driven sail. The sail, propelled by powerful lasers, would accelerate the spacecraft to a significant fraction of the speed of light, allowing for a journey to Alpha Centauri in a matter of decades. 3. NASA's nuclear thermal propulsion studies. NASA has explored nuclear thermal propulsion for potential Mars missions. The Nuclear Thermal Rocket Element Environmental Simulator (NTRES) tested components of nuclear thermal engines, and recent studies have revisited the concept for interplanetary travel. Challenges and considerations. While breakthroughs in propulsion hold incredible promise, they also come with substantial challenges. Nuclear thermal propulsion requires the development of reliable and safe nuclear reactors for space applications. Fusion propulsion involves controlling and sustaining extremely high temperatures and pressures, akin to those in the Sun's core, which poses significant engineering hurdles. Conclusion. Breakthroughs in propulsion technology are a beacon of hope for significantly faster space travel and more efficient exploration of distant galaxies. By leveraging the immense energy released from nuclear reactions, whether in the form of nuclear thermal propulsion or fusion propulsion, we could overcome the limitations of conventional propulsion systems and unlock the cosmos in ways that were once confined to science fiction. Let's explore the concepts of interstellar arcs and generational ships in greater detail and discuss the potential implications for intergalactic travel. Interstellar arcs and generational ships. Interstellar arcs and generational ships are visionary concepts that address the immense timeframes associated with intergalactic travel. Instead of aiming to complete the journey within the span of a single human lifetime, these concepts propose that multiple generations of travelers will live, work, and reproduce aboard the spacecraft, ultimately reaching the destination. Interstellar arcs. An interstellar arc is a self-contained spacecraft designed to sustain human life for the duration of an interstellar journey, which could span centuries or even millennia. The arc would need to provide not only the means for survival, food, water, air, and protection from radiation, but also an environment that supports social, psychological, and cultural needs. Generational ships. A generational ship is a specific type of interstellar arc where the journey is expected to take multiple generations to complete. Instead of aiming to travel at extremely high speeds, which is a significant technological challenge, generational ships embrace the reality of long journeys and focus on creating a sustainable ecosystem that can support a growing population over time. Implications for space travel. 1. Addressing time dilation. One of the advantages of generational ships is that they can effectively address the time dilation effect. Since the travelers on board experience the passage of time at a normal rate, they would not be subject to the extreme time differences associated with near-light speed travel. 2. Reducing technological challenges. Generational ships sidestep some of the technological barriers associated with achieving relativistic speeds or manipulating space-time. Instead, they rely on sustainable ecosystems and technologies that can be developed over time. Examples and considerations. 1. Project Longshot. Proposed in the 1980s, Project Longshot envisioned sending a generational starship to Alpha Centauri. The ship would carry multiple generations of travelers and could take several centuries to reach its destination. 2. Project Icarus. This is a modern iteration of the interstellar arc concept. It envisions a starship propelled by fusion or antimatter engines, carrying a crew of hundreds or even thousands of people. The ship's inhabitants would establish a self-sustaining society, adapting to the challenges of life in space over multiple generations. 3. Cultural considerations. One of the challenges of generational ships is maintaining a cohesive culture and society over the course of multiple generations. Designing systems that foster a sense of identity, continuity, and cooperation among the inhabitants is crucial. Ethical and psychological aspects. Both interstellar arcs and generational ships raise ethical and psychological considerations. Is it ethical to send generations of people on a journey with no chance of returning? How do you ensure that subsequent generations willingly continue the journey and don't rebel against the circumstances they were born into. Conclusion. Interstellar arcs and generational ships provide a unique approach to intergalactic travel, acknowledging the vastness of space and the limitations of current propulsion technologies. While they introduce challenges related to sustainability, ethics, and maintaining social cohesion, these concepts offer a way to bridge the gap between our current technological capabilities and the dream of exploring distant galaxies. By creating self-contained ecosystems that evolve over generations, humanity could embark on an enduring journey into the cosmos. Let's delve deeper into the role of quantum mechanics in the context of space travel and intergalactic exploration, and explore how it could potentially impact our ability to travel through space at greater speeds. The role of quantum mechanics. Quantum mechanics is a branch of physics that deals with the behavior of particles on the smallest scales, such as atoms and subatomic particles. While it might seem unrelated to the vastness of space and intergalactic travel, quantum mechanics holds intriguing concepts that could potentially revolutionize our understanding of the universe and impact our ability to travel through space. Quantum entanglement. One of the most intriguing phenomena in quantum mechanics is quantum entanglement. When two particles become entangled, their properties become correlated in such a way that the state of one particle instantaneously affects the state of the other, regardless of the distance between them. This phenomenon has been experimentally verified and has led to discussions about its potential implications for space travel and communication. Implications for space travel. While quantum entanglement cannot be used for faster than light travel directly, it could have implications for communication between spacecraft, which is vital for intergalactic travel. 1. Instantaneous communication. If we can establish a pair of entangled particles, one on Earth and one on a spacecraft, it might be possible to instantaneously communicate information between them, regardless of the vast distances separating them. This would overcome the limitations of light-speed communication, which can introduce significant delays. 2. Remote control and coordination. Entanglement could potentially allow for remote control of spacecraft, enabling rapid adjustments to flight paths, course corrections, and other operational tasks without time delays. Quantum teleportation. Quantum teleportation is another concept within quantum mechanics that sounds like science fiction, but has been experimentally demonstrated. Quantum teleportation involves the transfer of quantum information from one location to another without the physical transfer of particles. While this is not about physically moving objects across space, it does offer intriguing possibilities for information transfer. Implications for space travel. 1. Data transmission. Quantum teleportation could be used for secure and instantaneous data transmission between spacecraft and back to Earth. This is particularly relevant for transmitting large amounts of data collected during intergalactic missions. Examples in research. 1. Quantum communication experiments. Various research groups around the world are working on quantum communication experiments, involving the entanglement of particles and the testing of communication protocols that leverage quantum properties. 2. Quantum teleportation experiments. Experiments involving the teleportation of quantum states have been successfully carried out using particles like photons. While these experiments are currently limited to the realm of subatomic particles, they demonstrate the potential of harnessing quantum phenomena for information transfer. Challenges and considerations. Quantum mechanics is a complex field, and while its concepts hold immense promise, there are challenges to overcome. 1. Decoherence. Entangled states are delicate and easily disrupted by interactions with the environment. Maintaining entanglement over long distances and in challenging space environments is a significant challenge. 2. Energy requirements. Creating and maintaining entangled states might require significant energy resources. Conclusion. Quantum mechanics offers intriguing possibilities for space travel, particularly in terms of communication and information transfer. While we're not yet at a point where quantum mechanics can enable us to travel faster through space, it could revolutionize the way we communicate, coordinate, and gather information during intergalactic missions. As our understanding of quantum phenomena deepens, it's possible that these concepts could play a significant role in the future of space exploration. conducting a comprehensive breakdown of the total cost for the complete research. Intergalactic travel is a complex endeavor, as it involves a multitude of factors, technologies, and uncertainties. However, I can provide you with an overview of the major cost components that would likely be involved in such research. Please note that the figures provided are for illustrative purposes and should not be taken as accurate estimates. 1. Research and development. The research phase involves theoretical studies, simulations, and experiments to explore new propulsion methods, materials, and technologies. Costs would include salaries for researchers, equipment, facilities, and computing resources. Estimated cost, $500 million minus $1 billion. 2. Prototype development. Creating and testing prototypes of propulsion systems, spacecraft, and technologies for intergalactic travel requires significant investment. Costs include design, fabrication, testing, and iteration of prototypes. Estimated cost, $1 billion minus $5 billion. 3. Testing and validation. Thorough testing and validation are essential to ensure the safety, reliability, and performance of propulsion systems, spacecraft, and associated technologies. This phase involves ground tests, simulations, and possibly suborbital or orbital tests. Estimated cost, $1 billion minus $3 billion. 4. Mission development. Designing and planning an actual intergalactic mission involves intricate calculations, trajectory planning, mission architecture, and payload integration. Estimated cost, $500 million minus $1 billion. 5. Manufacturing and assembly. Building spacecraft capable of intergalactic travel involves advanced manufacturing techniques, specialized materials, and precision engineering. Estimated cost, $1 billion minus $2 billion. 6. Launch and deployment. The cost of launching spacecraft into space, whether through traditional rockets or novel propulsion systems, is a significant expense that varies based on the destination and mission requirements. Estimated cost, $500 million minus $1 billion per launch. 7. Mission operations. Operating and maintaining spacecraft during intergalactic missions involve ongoing expenses for communication, monitoring, navigation, and problem solving. Estimated cost, $100 million minus $500 million per year. 8. Ethical and legal considerations. Addressing ethical, legal, and regulatory aspects related to sending humans on intergalactic missions requires careful consideration and resources. Estimated cost varies. 9. Unforeseen expenses. Research and exploration projects of this magnitude often encounter unexpected challenges and expenses, necessitating contingency funds. Estimated cost varies. Total estimated cost range, $5 billion minus $20 billion or more. Please note that these estimates are speculative and could vary significantly based on technological breakthroughs, economic conditions, project scope, and the involvement of public or private organizations. The actual cost could be higher or lower than the provided range. Keep in mind that intergalactic travel is a highly ambitious and long-term endeavor. The costs involved would depend on the pace of technological advancements, the commitment of resources, and the determination of humanity to venture beyond our solar system. Feel free to ask if you'd like more information or a deeper exploration of any specific aspect. Thank you for being with me for this whole time. See you on next video.